2015 AP Chemistry Free Response question number 5. So this question is looking at the oxidation of blue food coloring with bleach, and is tracking it using a spectrophotometer set at a wavelength of 635 nanometers to study the absorbance and how that changes over time. So we're given graphs of the students' data, 3 different graphs of absorbance versus time, the natural log of absorbance versus time, and the inverse of absorbance versus time. So remember that absorbance is directly related to concentration. So although the mathematical values for the absorbance and the concentration would clearly be different numbers, how they change over time is going to look pretty much exactly the same. So in terms of trends in how they change, we can use absorbance and concentration more or less interchangeably. So the first thing we're asked is, based on the graphs above, what is the order of reaction with respect to blue food coloring? So looking at our 3 graphs, we have absorbance versus time here, we have natural log here, we have inverse. That's really ugly. Let's try again. We have inverse here. So we know that one way that we can determine the reaction order is by looking at which of the plots is linear. If this one were linear, that would represent a 0 order reaction, but it's not. If this one is linear, which it is, that's a first order process. If this one's linear, which it's not, it would be a second order process. So the linear graph for us is the natural log of absorbance versus time, which is consistent with this being a first order process. Note that you weren't asked to explain how you know, you were just asked what is the order. So first is a complete answer here. You do not need to say anything else about it. The next part here says the reaction is known to be first order with respect to bleach. In a second experiment, the student prepares solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near 0 too rapidly. In order to correct the problem, the student proposes the following 3 possible modifications: increasing temperature, increasing concentration of food coloring, increasing concentration of bleach. And we're asked to circle the one proposed modification that would actually correct the problem and explain how that modification increases the time for the reaction mixture to reach an absorbance near 0. So we're looking for something that's going to make it take longer for our absorbance to drop. Now remember that absorbance is related to color. So the absorbance is telling us the concentration of our blue food dye, this big molecule here. So the higher the concentration of that molecule, the higher of our absorbance is. The bleach molecule, this guy in here, is colorless. So the concentration of bleach isn't affecting the absorbance. Only the concentration of our blue food dye is actually affecting that absorbance value. So we want something that's going to make it take longer for the absorbance to reach 0. So increasing the temperature generally increases the rate of a reaction, makes it go faster. If we're not changing anything else, making our reaction go faster is going to use up our food dye even faster, making it take less time, not more, for us to get an absorbance near 0, which is the opposite of what we want. Increasing the concentration of food coloring. If we start with more dye to begin with, if we start with more food coloring initially, it's going to take it longer to use up if everything else is being held constant. So this is the correct choice. And the explanation is that if more food dye is present to start, it will take longer to use it up. So we simply have more stuff. We're starting at a higher concentration, also means we would start at a higher absorbance. So it's going to take us longer to get down to an absorbance that's near zero. Just for completion, let's talk about the last option, increasing the concentration of bleach, and why that would not be effective in accomplishing what we want. So if we're increasing the concentration of bleach, but not food dye, so if that's the only thing we're changing, we're told up here that the reaction is known to be first order with respect to bleach. That means increasing the concentration of bleach is increasing the rate of our reaction. If we're increasing the rate of our reaction, but we haven't added more food dye, we're going to use up that same amount of food dye more quickly. We're looking to make this take longer, but increasing the concentration of bleach would also make it take less time. So this one would be counterproductive as well. So then in part C, we're told in another experiment, a student wishes to study the oxidation of red food coloring. Let's change colors, because why not? Red food coloring with bleach. How would the student need to modify the original experiment procedure to determine the order of reaction with respect to the food coloring? So the only difference here is the color, is that we're dealing with a red dye instead of a blue dye. When we see something as a different color, that means it's absorbing different wavelengths in the visible spectrum. And we always want to make sure that we're recording the wavelength of maximum absorption or something close to it. So the wavelength most absorbed by a red dye is going to be very, very different than the wavelength most absorbed by a blue dye. So the only thing this student has to change is that they need to set the spectrometer, or spectrophotometer, to record at a different wavelength. And again, we weren't really asked to explain anything in this part of the problem, so that's all we need to say. Set the spectrometer to a different wavelength, done. We were told up here that for our blue dye, we studied 635, which is a reddish wavelength. If we see something as blue, blue is what's not being absorbed, and we want to measure what is. So if you wanted to be a little bit more specific in part C, you could say that you might want to set it to a wavelength somewhere in the blue to purple region of the spectrum would probably be reasonable, but you don't even need to get that specific with it. You would just need to specify at a different wavelength. And you might want to throw in whatever is most absorbed by the red dye, or most strongly absorbed. But that is a totally good and complete answer.